Okay, I'm back. My director was warning me that our battery on the camera was going out. So here I am again, and let's talk about kimberlites. Kimberlites are another type of igneous ore deposit, and it's a special type of volcanic breccia. Remember from igneous rock lecture, a volcanic breccia is formed from an explosive volcanic eruption where the volcanic material gets all broken apart into little bits and pieces. And this is a kimberlite up in Michigan. And if we zoom in on that kimberlite and look closely at it, you can see all those different little bits and pieces in there. Now, what makes kimberlites special is that they come from the mantle. This is basically volcanic material that rises very quickly from the mantle, possibly traveling as fast as tens to hundreds of miles per hour from the mantle upwards to erupt on Earth's surface. And as this magma rises very quickly from the mantle upwards, it can pick up some hitchhikers along the way. And those hitchhikers happen to be diamonds. So the diamonds aren't actually formed in the kimberlite, but as the kimberlite rises upward, it sort of kidnaps some of them and brings them to the surface. Now, not all kimberlites contain diamonds, because diamonds form under specific temperature and pressure conditions. And diamonds also are pure carbon, so you need enough carbon in the mantle, you need the right pressure, you need the right temperature. And so if you have this diamond-bearing part of the mantle and the kimberlite rises upwards through that, well then you'll have diamonds in that kimberlite. But if your kimberlite doesn't rise through one of those diamond-bearing parts of the mantle, it will not have diamonds in it. Now, your typical kimberlites have kind of this carrot shape to them, and that's where we would extract the material to find those diamonds in there. And anyway, that's kimberlites. I'm not that fond of diamonds. I think they're a scam, but you can ask me about that sometime. But let's move on to our next igneous intrusion. And this is a plain old igneous intrusion. It is not coming from the mantle, it is not layered in any way, it's not the last part to cool, it's simply granite or gabbro or something like that. But it does have a few special characteristics. It has to look nice. And we don't want it to have a whole lot of fractures or cracks in it. And the reason for that is if it looks nice, doesn't have a lot of fractures in it, it can be something we call dimension stone. It's called dimension stone because you can order like a block of it. You can go and say, hey, I want a piece of this granite that's like 2 feet by 2 feet by 3 feet, and they'll cut you a piece of it. Right? We cut it to those dimensions. And what do we use it for? This is used for things like your countertops. If you're able to afford granite countertops, well, that's your dimension stone. It's this cut granite, cut and polished, and then used for that. It's also used for monuments and buildings. This is a dimension stone quarry in Marble Falls, Texas. They are extracting granite from there. Notice you can see these very clean cuts right there, and that's because they cut blocks of granite out of there. And in fact, the granite that was used to build the state capitol in Austin comes from this quarry. So that's our dimension stone. Now that's the only igneous ore deposits that I wanted to talk about. There are others, but we're simply going to leave it at those. And now let's move to another way that ore deposits can be formed. And this next way are hydrothermal ore deposits. Again, hydrothermal, thermal refers to heat, hydro refers to water. So in this case, we have hot water flowing through rocks, depositing minerals. And one of the things you might get is something called a vein deposit. A vein deposit is a tabular body of minerals precipitated in cracks. Remember, tabular means like a book. So basically it's thin in one dimension, is much longer in the other dimensions. And this is different from a dike. It looks kind of like one, but it's different from one because remember, a dike is made from igneous rock. One of these veins is made from minerals. And what happens as this hot water flows through these cracks in the rock, it starts cooling down. Hot water can hold more material in solution than cold water. So as that water cools down, as it's traveling through those cracks, it is going to end up precipitating, leaving behind minerals in those cracks. And that's exactly what we have here. This comes from a manganese mine in New Mexico, and this is a crack in the rocks there, and hot water flowed through it and left these minerals behind. Now, many vein deposits have precious metals in them, like gold and silver. But you can find other minerals in there as well, like I did just show you a manganese mine. So obviously that's something that can be deposited as well. Generally, because the minerals are concentrated in a certain area, when you have these vein deposits, you use a technique of mining called underground mining. Basically, you follow that vein into the ground. And you might do that by following a shaft underground. This is called a shaft house. It sits on top of a mine shaft. Basically, it's like an elevator, right? An elevator has a shaft that goes up and down. That's what's going on in here. There's cars that would raise and lower people and bring ore from underground. You can also enter a mine, an underground mine, through what's called an adit. Adit is spelled A-D-I-T. And an adit is basically like a tunnel. And so this is an adit going into the ground following some of these concentrated ore deposits. And that's what an underground mine looks like. This is the Quincy mine in Michigan. This is where my husband used to work, and they extracted copper out of this mine. And that is the adit going into the mine there. Now, hydrothermal ore deposits don't have to be in these veins, and these veins can be anywhere from a few centimeters to some meters in size, in width. They don't have to, hydrothermal deposits don't have to be in veins. We can also have disseminated deposits created. Sometimes these are also called porphyry deposits. I prefer the term disseminated. Just disseminated means scattered around, and that exactly describes these ore deposits. In this case, the ore minerals, the valuable minerals, are scattered through a large body of rock along tiny, tiny, oftentimes microscopic cracks. This is some ore from a disseminated deposit. And this comes from the Newmont Mining Company, so this is actually gold ore, but the gold in there is, it's really microscopic. It's not this stuff, that's actually iron. You can't see it without a microscope, but it's scattered through a huge volume of rock. So how do we extract this stuff? Well, we use something called an open pit method in order to extract oftentimes copper, molybdenum, and sometimes those precious metals. And like I said, in this case, we're going to use an open pit method where we just dig into the ground and try to extract as much of that rock that's holding those microscopic little bits of ore. And this is Bingham Canyon Copper Mine in Utah. My dad did some work out there many years ago. This is the largest open pit mine in the world, sort of. It is about 2.5 miles across, and it's about 3/4 of a mile deep. And they've been digging their open pits since, I believe, 1906 or somewhere in the early 1900s. And I did say it's sort of the largest open pit mine because there are others that are equally large, like Escondida in Chile and Morenci in Arizona. So those were the two hydrothermal ore deposits I wanted to go over. There are others that exist, but for the sake of class, just realize that vein deposits, the valuable minerals are concentrated in a very specific area, and in disseminated deposits, they're scattered throughout a large volume of rock. And that allows me to move on to another ore deposit type, and this is sedimentary ore deposits. So in this case, the rock that we are getting out of the ground that holds these valuable minerals is sedimentary rock. I'm going to start with banded iron formations, like this. This is a banded iron formation. And banded iron formations we call BIFs because geologists are lazy and don't feel like saying banded iron formation over and over. This is what a banded iron formation looks like. Banded referring to those layers that are in there, and then iron, of course, that's what we get from these. Banded iron formations only formed in the Precambrian. And they only formed in the Precambrian because we had some very specific conditions on Earth at that time. So early Earth's atmosphere had no oxygen in it. It had no what we call free oxygen, O2, the stuff that you and I breathe. And in the Precambrian, photosynthesis began. Photosynthesis, the byproduct of it is oxygen. So what we see in the Precambrian is Earth's atmosphere goes from having no oxygen in it to having oxygen in it. We call it the Great Oxidation Event. And why this is important for banded iron formations is when, now I'm putting this in a nice simple way, of course everything's more complex, but in the very basic way, when there's no oxygen in Earth's atmosphere, when there's no free oxygen, iron is very soluble in water. So back in the early Precambrian, we get lots of iron in the water because it's really, really soluble. But as oxygen is added, due to that photosynthesis, iron loves to bond to oxygen. It's just like, hey, oxygen, and it bonds right to it. But when it bonds to oxygen, it becomes insoluble. And so as photosynthesis was producing this oxygen, the iron was bonding to this oxygen, becoming insoluble and precipitating from the water of the Earth's oceans, creating these banded iron formations. So this is something that only happened in the Precambrian and won't happen again because in order for it to happen again, we'd need Earth's atmosphere to get no oxygen in it again, so iron could build up great amounts in the oceans, and we definitely wouldn't want that to happen, right? We need oxygen. So this happened once upon a time and is not going to happen again. But sedimentary rocks sedimentary rocks can create other types of ore deposits. We can have these placer deposits forming. And in placer deposits, the ores are concentrated by flowing water. Remember, as long as water is flowing, it has the energy to pick up particles. And as water slows down, it loses the energy and it's going to start dropping off big or heavy particles first. So placer deposits are going to be heavy ores. And something that happens to be very heavy is gold. So what we might see in a placer deposit, we have this stream flowing along here, and wherever the water slows down and loses some of that energy, it's going to start dropping the minerals, the gold. And in streams, water flows fastest at the outside of a curve and slowest at the inside of a curve. So if you are looking for placer deposits of gold, you would look for it anywhere where water slows down in a stream. Now, if any of you guys have gone gold panning, you are kind of artificially creating a placer deposit. So the way gold panning works, you take a bunch of sand and water and you swirl it around this gold pan. And as you're swirling it around, that's energy, right? So that's going to be lifting up the lighter sand and kind of tossing it out of the gold pan. And what doesn't get lifted up are the bigger, heavier pieces, and amongst those heavier pieces are going to be pieces of gold. So that's our placer deposits. And there are many, many other types of ore deposits out there. Some metamorphic rocks create important geologic resources. Other sedimentary rocks create important geologic resources. I just really do not have the time to cover all of those. So we're going to move on into energy resources. The energy resources we're going to be covering include coal, uranium, and hydrocarbons. Hydrocarbons are oil and natural gas. And they're called hydrocarbons because these are chains of carbon atoms bonded together, and then on those carbon atoms there are hydrogen atoms bonded as well. So hence hydrocarbons. We're going to begin with coal. Coal is made from the remains of land plants that did not completely decompose. Normally, when leaves fall off trees or when branches fall down, bacteria and fungi will decompose that and basically the material disappears. But in certain environments, that organic material won't decompose and it will start to accumulate, which is what we're seeing here. All this dark material right there, that's something we call peat, and that is an accumulation of many years of this organic material. Now, why don't things completely decompose? Usually it has to do with stagnant water, water that has low or no oxygen in it. Because when we reduce the oxygen, we reduce the decomposition. And places where we tend to get that are in swamps and bogs. So if I was thinking of places where coal would be forming today in the United States, I think of places like southern Louisiana where it's very swampy, or South Florida where it's very swampy. Now, coal does have different grades. When we talk about grades of coal, it's kind of a grade refers to how good something is. So lower grade coal, if we burn a chunk of this lower grade coal, it will produce some energy and a whole lot of waste. If we burn a higher grade of coal, it'll produce a lot of energy and less waste. So I have listed here from lowest to highest grade of coal. So we have peat, which actually forms on Earth's surface. And if you see peat, you'll actually still see like little leaves and roots and stuff in there. And we have lignite, which is called brown coal. This is a little bit better than peat, but still not the highest energy content. Then we have bituminous coal. Bituminous coal is very much what most people think of coal being like. It's this sort of chunky black stuff. And then we have anthracite. Anthracite is a very shiny black coal. It contains the highest energy and produces the least amount of waste. So that would be the highest grade coal. And that's what I have shown here, how this coal forms. We get the peat forming on the surface, and then as this material gets buried and it gets compacted, the carbon in there gets concentrated, and so we go from this lowest grade peat to this highest grade of anthracite. This is what some coal looks like. Every now and then you'll get these like petrified things in there. There's a stump of a tree that the entire stump has been turned into coal. And the U.S. has the most coal deposits in the world. We have a huge amount of coal, but we are moving away from using that coal. It has traditionally been used to generate electricity. And the way a coal burning power plant works is you burn the coal to heat water. The water is turned to steam. The steam turns a turbine, and the turbine turns a generator, which makes electricity. But the reason we're moving away from using coal is because there are byproducts to using coal. And some of the issues with using coal include solid waste. You get something called fly ash. Just think about if you have like a campfire or something. At the end of the night, you have a whole bunch of ash left over. Well, same thing happens in power plants. You burn the coal, you have a whole bunch of ash left over, and that has to be disposed of somehow. Now, some of it is used in making concrete, because by adding a certain amount of fly ash, you get different characteristics to concrete. But not all of it can be used for that, so the rest has to be disposed basically in like landfills. Also, when you burn coal, it emits sulfur dioxide, which can cause acid rain, and carbon dioxide, which is a greenhouse gas. An additional issue with coal is the mining methods can be quite disruptive to Earth's surface. In fact, in some cases, strip mining is used, and this is where the coal is very close to Earth's surface. So you basically peel away the soil, and then you scrape away the coal, and then you basically reclaim the land, put the soil back, plant native plants and things like that. But because there are these issues, people are trying to get away from using coal. This is a mine. If you drive north on US 59, drive northward here in Texas, and you'll get to the Martin Lake mine. This is a strip mine. This is called a drag line. That's the thing that drags along the surface, scraping up the coal that will be used. Coal can also be mined underground. This is an underground coal mine. Let's go underground. Notice this underground coal mine looks significantly different from that underground copper mine that I showed you earlier. And that's because this is in sedimentary rock. Remember, sedimentary rock forms in layers. Those layers have a tendency to collapse. So when you're in these coal mines, you'll see lots more timbering and support against those mine collapses. Coal mining is also one of the most dangerous kinds of mining because coal mining ends up, coal being an organic material, it can produce, you can get these weird gases in coal mines. You can get methane, which is flammable, and then you can get things called, that the miners call these things like black damp and white damp, and they're mixtures of carbon dioxide, carbon monoxide, and nitrogen. And no oxygen, so that's really bad because, again, we need oxygen to breathe. So what this guy's doing right here, we can see we have this coal seam, this coal deposit right there, and he has a safety lantern. And the safety lantern allows the atmosphere to enter, and there's a little flame in there, but it does not allow the flame to leave. And he is checking for methane, which, like I said, is flammable or in the right abundance explosive. And methane is lighter than the normal atmosphere, so it'll tend to accumulate at the top of the mine tunnel. And so he holds the lamp up there, and since it's flammable, that little flame in there, if there's methane present, will grow. It'll get bigger. Now, as far as black damp and white damp, he can check for that with the flame as well. But those mixtures of gases are heavier than the normal atmosphere, so they'll start to accumulate down by his feet. So he'll take that safety lantern, hold it down by his feet, and because fire also needs oxygen, if there's no oxygen, the flame will start to go away. And if either one of those circumstances is going on, he knows to get the heck out of the mine. Now, of course, in modern mines, there are many modern high-tech ways of keeping track of the atmosphere, but lots of people do still like to have their safety lanterns. So coal mining is quite dangerous, which is one of those additional issues with using coal. But that being said, I do want to show you a coal-fired power plant. This is in summertime when this thing is operating at full power. And one thing you'll notice, you don't see those giant billows of steam and smoke coming out of there, because you can put scrubbers on the stacks, which will capture much of the sulfur dioxide and other emissions. Will not capture the carbon dioxide, however. But what I'm trying to get at is, if you're willing to invest the money, you can make coal a cleaner energy source. But that is a cost-benefit analysis that people need to think about. How much are they willing to pay to make things cleaner? And I'll see you in volume 3 of Mineral Resources when we talk about the other energy resources.